time for some note taking for today's lesson about primes and composites. So again, this is that notes packet that you should take with you wherever you go. It should already say save on the top. It should probably say it's not homework. And it should even say bring every day. And your name, date, and hour should be on there. Let's pretend you don't have this fabulous notes packet. I guess you're getting out some lined paper now. So get yourself situated so that you can take some notes with us. We are moving on to lesson 1.2. That's really what we practiced with those prime and composites in your game today. So I want you to turn in your notes packet until you see 1.2 prime factorization at the top. It looks something like this. And I do have to apologize because our copies didn't print really nice. So it's kind of maybe harder to see than it should be. So this really says slide 1 learn, and it looks like they're trying to take this 18 and break it into some factors. This isn't usually how we show factors of a number. Instead, we usually do a t-chart. So off to the side, I'll just think of a t-chart here. And 18, I don't think that was on our practice problems today, but you should be thinking, well, 1 times 18 will work. You can go back to your rules and find that this ends in 8, so it probably divides by 2. Let's see, 2, 4, 6, 8, 10, 12, 14, 16, 18. That's 9 tallies. 2 times 9 is 18. Will 3 work? Oh, remember the rule? 1 plus 8. Does that equal something that will divide by 3? Oh yeah, 9 divides by 3. 3 will work. But 3 times what? So counting by 3s, you could say 3, 6, 9, 12, 15, 18. Looks like I made 6 tallies. It's like 3 times 6 is 18. Should I try 4? Well, 4 will work, especially if 2 times an even number got me to 18. But 9's not even, is it? So I don't have to worry about 4. And 5, well, it doesn't end in 5 or 0. And if you notice, it takes me right back to the 6, meaning, yeah, I've tested everything I need to. These are all in a sequence or an order that tell me I have all the factors. So how many factors did we find? 6. One, 2, 3, 4, 5, 6. And down here they asked me to print which factors I see. Another way of showing this would be right over here. Same idea. Just in a list. A different type of list. So the factors of 18, let's put them in order. Well, 1 works, 2 works, 3 works, 6 works, 9 works, and 18. And notice I'm going from least to greatest to be organized in my list. Next it says find the prime factors of 18. That means which of those numbers in here are prime. Well, 1, it kind of looks tricky. It looks like it might be prime, but if you think back, that's actually considered a special number, not 1. How about 2? Think back, is 2 on that list of prime numbers we should remember? Sure is, because only 1 times 2 will work for 2. How about 3? Prime or composite? You should be saying prime. It goes on this prime factor list. 6? Prime or composite? It's composite. It's an even number. Not only 1 times 6 works, 2 times 3 works too. 9? Oh, don't be fooled. It might be odd, but it is composite. 1 times 9 and 3 times 3 has too many factors. And 18, well, yeah, it had all of these factors, so I would guess 18 must be composite. We only have 2 prime factors. These are special. They're prime. Today you get to stretch your thinking a little bit more with primes and composite numbers. So you're going to be given a composite number, and we're going to write it as a product of its prime factors. So there are 2 methods here. This one is called a ladder method. It kind of looks like a ladder. Kind of like we're climbing down the ladder. And over here, this is considered a factor tree method. So let's give this a try. Here's the real challenge with ladder method. This is why some people won't choose it. The number you put over here or choose to go on the side has to be prime. Has to be prime. Must be prime. Okay? So we need to think of what kind of prime number will go into 60. Well, I see it's even, and 2 is a prime number, I know. 2 will work. 2 times what? 30. So it's almost like I'm doing upside down division here. 2 goes into 60 30 times. And I wish my Copy was a little bit better for you. I hope you can see this. Well, now I have 30 to work with, and I want to break it down again. I need to think of a prime number, have to choose a prime over here, that will go into 30. Oh, 2 will work again, won't it? 30 is even, ends in 0. Okay, 2 goes into 30 how many times? 15 times. I'm getting there with this idea of a ladder method. 15 can be broken down again into some other factors. I don't want to put 1 over here because 1 isn't prime. I don't want to put 2 over here because 15 isn't even. But I do know that 3 goes into 15. I could put a 3 here. And 3 goes into 15 5 times. You have just found me the prime factorization of this number. Meaning I could take everything over here from my ladder, everything to the side in the bottom of my ladder, and rewrite it as a factorization. I could write 60 equals 2 times 2 times 3 times 5. And notice in factorization, I use multiplication. And it's not the multiplication symbol that some of you like, but I'm saving the X for algebra. So here's one way of showing that prime factorization. What this really means is I could check it. 2 times 2 is 4. 4 times 3 is 12. And 12 times 5 actually would get you 60. This would work. There's another way to factor 60 and find its prime factorization. We can use a factor tree method. The reason why people like factor tree methods is because you can really choose any number that divides into 60 nicely. It doesn't just have to be prime. So maybe you're thinking to yourself, 6 times 10. We put the 6 and the 10 on the branches of our factor tree. Well then, you say to yourself, is 6 prime or composite? Oh, it's composite. We're going to break it down into 2 factors. So what times what will get me 6? How can we break it down into what we're trying to get to, prime numbers? Well, 2 times 3 will work. And actually, 2 is prime, so I circle it. 3 is prime, so I circle it. This part of my tree is done. But over here I have this 10. Is 10 prime or composite? Oh, it's composite. We need to break it into 2 branches. Something times something gets me 10. Oh, I know. 5 times 2. And really, it wouldn't matter if you had the 2 on this side and the 5 on that side. It should still work out. Is 5 prime or composite? Prime. Circle it. Is 2 prime or composite? Prime. Circle it. Let's see if we can write this in an organized way. I keep going with this tree until I have only prime numbers at the bottom encircled. There, my tree is done. I just want to organize my factors. So I only circled prime numbers. I only include those circled numbers, and I put them in order. 2, 2, 3, 5. And remember, factorizations can use multiplications. So I'm using multiplication here. And again, if you look, I got the exact same answer either way, ladder method or factor tree method. One more stretch of thinking for someone who likes it. Do you notice how I have 2 of these? We could use something called exponential form. So I'm going to try to show you that now. Another way of listing this would be 60 equals 2 to the 2nd power, because there were 2 of them, times 3 times 5. And again, I'm not using the evil x, saving x for algebra. I'm using multiplication symbol, a different type. So both of these are good answers. You have found me the prime factorization of 60. Turn your page to slide 3. It's your turn. It says journal reflection. Which method will you use to find, or I should say to find, the prime factorization of 36? So you can either try what's called a ladder method. Be careful, you have to choose a prime number over here, or a factor tree. This would probably be a good time for the guest teacher to put me on pause and for you to try it, and then come back and see if we are in agreement, make some changes or some additions to your work. I bet you're back. I need to choose a prime number here. I'm thinking of 3, because I know 3 times 12 will work. Well, 12 is still composite. I can break it down again. What prime number goes into 12? Oh, 12 is even. I could put a 2 over here. 2 times 6 would work. So 2 goes into 12 6 times. Uh-oh, 6 is still composite. I can break it down some more. And I don't want to use 1. 1 is special. I could use 2. 2 goes into 6 3 times. It's like this upside down division. And you know what? 3 is prime. So I'm going to take all of these and circle them. I found my prime factorization. I just have to organize it. Let's see if I can do the same thing with 36. Let's see. Maybe you know 4 times 9 will work. 4 times 9. That's good. So on my factor tree, I show 4 on one branch, 9 on the other. Well, neither one is prime. Both are composite. We need to break them down again. So 4 is the same as 2 times 2. And I remember something. 2 is prime. So I circle this 2 and I circle that 2. How about 9? I'm trying to break it into prime numbers. 9 is the same as 3 times 3. And actually, I remember back from my list, 3's are prime. How would I write out this factorization? 36 equals, well, we take our factors in order. So whether I look here at my ladder method or here at my tree method, I could show you that I have 2 2's, 1 2, and I have 2 3's. And it's a factorization, so you're going to show me multiplication. What if some of you like that idea of exponential form? You could show me another way of indicating your factorization. You could say there are 2's, how many? 2 of them. You could say there are 3's, how many of them? 2 of them. This is considered a prime factorization using exponential form. So both of these are good answers. They both are true. I really expect you to break down the steps now. So you could say, to find the prime factorization of 36, and carry on with a thought here if you haven't started writing yet. I did what? I used a ladder method and explained how it works. Or I used a factor tree method and explained what you found or how you split it up. So either way, you need to explain for me your steps here. Get ready, get set. We're given another composite number. They give me 48. And method 1, what's this called over here? Oh, that's right, a ladder. And over here, method 2, what's this called again? A tree. Oh yeah, I need to climb a ladder to get in the tree. Ladders and trees go together. Okay, I don't care which way you break this down, but again, if you choose method 1 in this ladder method, you have to put a prime number over here. It is a must, or it won't go well for you. So prime numbers. Oh, I like to see that this is even. 2 will work. 2 goes into 48 24 times. And hey, 24 is even again. 2 goes into 24 12 times. And 12 is even again. 2 goes into 12 6 times. I'm working my way down this ladder. And guess what? 6 is still even. 2 goes into 6 3 times. Hey, 3 is prime. I must be to the bottom of my ladder. An L for this ladder method. There we go. We have to try the same thing, but we're going to try it with this factorization tree. So 48. Well, I'm thinking of it differently. I think 12 will work. 12 times 4 is good. You might have chosen some different factors here. As long as they multiply to 48, you're good to go. Well, 12 is considered composite. I can break it down. 4 is composite too. I need to branch it into 2 parts or 2 factors. And I'm trying to get to prime factors here. So I know that 12 is even. 2 should work. 2 times 6 is good. Notice that Math and Focus uses this multiplication dot for you. If you like to put that there, you can. Well, 2 is prime, circle it. 6 is not. I need to break this down some more. So what factors will work for 6? Oh, I know. 3 goes into 6, and 3 is prime, so this is good. And 3 times 2 will work. Is 2 prime or composite? Prime, circle it. We have to do the same thing with this 4. Make sure you go back and finish all of your branches. You have to make some leaves before you're done. So 4 could be split into 2 times 2. And I'll use that multiplication dot because Math and Focus would show it in your book that way. Well, 2's are prime, so I circle them both. And Math and Focus even would bring these down to the bottom level just so that you don't miss anything. I personally don't always do this. But this way you see them all in a line. Problem is, They're all mixed up. And if you decide to bring them down, you don't want to climb back up the tree and grab those circled factors. That's kind of why I don't do that all the time. Here we go. 48. Let's write out its prime factorization with some multiplication. So I have a bunch of 2's. 1, 2, 3, 4 of them. 1, 2, 3, 4 of them. And I also have a 3. 3. I could also find that on my tree. Here's a 2, a 2, a 2, and a 2, and a 3. It absolutely works. What am I missing? Multiplication for factorizations. This is one good answer. And you could always check it. You could say, hey, what is 2 times 2? It's 4. What's 4 times 2? It's 8. What's 8 times 2? It's 16. And if you were to check, 16 times 3 would actually get you 48. It works. Maybe you like this idea of exponential form. What number gets repeated? Oh, there are a bunch of 2's. How many of them? 2 becomes my base, and the number of times I use them in multiplication becomes the exponent. And I'll multiply that times 3, but there's only one of them. I could put a little 1 behind the 3 as an exponent, or I can just leave it by itself as a base. It means the same thing. Either one is a good final answer. Next up, slide 4. I don't have to do the factorizations. They've done them for me. Take a look. It says 320 could be written as a product of its prime factors. Look at all those 2's and a 5. Then they say write 3,200 as a product of its prime factors, but don't use a ladder or tree. Are you serious? If I take a look, I might write this out. 320 is the same as everything they said here. How many 2's are there? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And there's also a 5 at the back. I don't have to test it. They say it's true. I just have to show it with multiplication in my own writing. And now they want me to change it into 3,200. And they don't tell me to use, or they tell me not to use, a ladder or a tree. Boy, if only I could figure out a pattern. How did they get from here to here? Oh, there's an extra 0 on the back. How did they go from 320 to 3,200 and get that extra 0? I hope someone out there is thinking, you could multiply by 10. And you're absolutely right. I don't have to make a factor tree to show that. I know that I could multiply all of these numbers and multiply 1 more times 10. So let's take a look at that. 2 times 2 times 2 times 2 times 2 times 2 times 5 times 10. Let's make sure I have it all. 1, 2, 3, 4, 5, 6 2's. 1, 2, 3, 4, 5, 6 2's, 1 5, and remember, we were going to multiply all of that by 10 to get that extra 0 at the back. I'm onto their trick. This would be an awesome final answer if this was a prime factorization. What's wrong with 10? Oh, it's composite. You need to break it down. We need to show it as a prime factorization instead. So I'm going to grab this 10 that they used to go from 320 to 3,200, and I'm going to break it into prime factors. Oh, 2 will work. 2 times 5. And actually, those are prime factors. This is the shortest tree I've ever made today. So I could go ahead and fix this. 3,200 is the same as all of the 2's I was given and an extra 2, and all of the 5's I was given and an extra 5. Let's try it. 2, 3, 4, 5, 6. 5, 6, 7. 1, 2. Remember, this is prime factorization, so you get to use some multiplication. This is really tiring to write. This is one good answer, but someone might like that exponential form because it goes a little bit quicker. How many 2's did you end up with? 1, 2, 3, 4, 5, 6, 7. 2 to the 7th power. It repeated 7 times. And how many 5's did we end up with? 5 to the 2nd power. The base is 5 and it repeated 2 times. So 5 to the 2nd power. And remember, factorizations get multiplications. Here's a good final answer. We have one more to go before you try it on your own. So it says in the journal reflection, which method will you use? I want to go from 1,000 to 100. They give me 1,000, and they ask me to find its prime factors. That's the question. And then they give me 100, and they already say, they broke it down for me. 2 times 2 times 5 times 5. Notice they use the X for multiplication. I don't like that. So I changed it to dots for multiplication. We're working this way right now. How would I go from 100 to 1,000? Or if you don't like that written up there, it might be easier to show it underneath. Maybe I should have done that. Too bad I'm not working in pencil like you are. How would I go from 2 zeros in 100 to 3 zeros in 1,000? Same trick as before. Looks like they took it times 10. So I get to steal every single factor they gave me. 2 times 2 times 5 times 5. But I'd have to multiply all that times 10. Awesome. Looks like I'm really close to an answer. But, alert, look at this 10. What's wrong with it? It's composite. I need prime factors, not composite factors. So we break it into some prime numbers. How about 2 times 5? Are those primes? Sure are. I'm ready for an answer. I know the prime factorization of 1,000 would be 2 times 2 that I was given times an extra 2 I found times 5 I was given with the extra 5 I need to use from my factorization of 10. This is a decent answer, and some of you are thinking, I could rewrite that. I could use a base of 2 and show it happened 3 times in my exponent, or a base of 5 and use an exponent of 3. Either one is a great answer, and you really could check this. If you multiplied it out, you should get back to 1,000. Let's see, 2 times 5 is 10, this 2 times that 5 is 10, and this 2 times the last 5 is 10. 10 times 10 is 100. 100 times 10 is 1,000. This would absolutely check out. Now we need to write about it. So explain what pattern you noticed. I noticed 1,000 was 10 times 100. So then what? Go ahead and explain your steps. What did you decide to do next? I think for today I'm going to let you stop with some note taking. Hopefully that's filled up your time and your pages quite a bit, and I'm going to give you a chance to work on some homework for the night.